even and odd functions. A function is called even when it is symmetric about y-axis. This can be given by a graph as, mathematically this can be given as, a function is called odd when it is symmetric about origin. The odd function can be shown as, mathematically an odd function can be given as, some of the properties of even and odd functions are, the sum or difference of two even functions is even. Let f and g are even function. Then their sum or difference is also even. The sum or difference of two odd functions is odd. Let f and g be two odd functions. Their sum or difference is also odd. The product of two even functions is even. The product of two odd functions is even. The product of an odd and an even function is odd. Related terms are, what is half-range series? When a function is defined on half of its period, the Fourier series of the function are called half-range series. There are two half-range series. Let us suppose a function fx. Let the period of the function be 2l. The function is defined only for. Now we extend the definition to. When the function is defined from 0 to 1, we call it an even periodic extension of fx. When the function is defined from -1 to 0, we call it an odd periodic extension of fx. If fx is given, an even extension is done, then fx is even and it has a Fourier cosine series. The series is given by, the coefficients can be given by, if fx is given and an odd periodic extension is done, then fx is an odd function and it has Fourier sine series. The series is given by, the coefficients are given by. Related terms are, what is Fourier series and periodic function? The series obtained when a given periodic function is expanded in an orthogonal series in terms of trigonometric functions is known as Fourier series. Let the periodic function be. Let the period of the function be. The series for the function can be given as. The notations used in the formula are known as Fourier coefficients. The Fourier coefficients can be given as. The expression for these coefficients are known as Euler's formula. If a function repeats itself after a certain interval, then the function is called periodic function. Let us assume the following condition for a function. This function is periodic and has a period of 2. Related terms are, what is Laplace transformation? It is a linear operator of a function ft with a real argument t greater and equal to 0, that transforms ft to a function fs with complex argument s. Mathematically, Laplace transformation is expressed as, where ft is the function with real argument, fs is the function with complex argument, t is real argument, s is complex argument. The Laplace transformation is applicable to piecewise continuous function. The piecewise continuous function is as shown. There is an alternate notation for Laplace transforms. For the sake of convenience, we'll often denote Laplace transforms as Related terms are What are the Laplace transformations of standard functions? The Laplace formula is given by, or the transformations of function with real arguments to function with imaginary arguments are known as Laplace transformations. We will now see the transformations of some standard functions. The transformations of function with real arguments to function with imaginary arguments are known as Laplace transformations. The Laplace transformation of sine function is given as, Laplace transformation of cosine function is given as, Laplace transformation of constant is given as, Laplace transformation of exponential function is given as, Laplace transformation of first order derivative is given as, the Laplace transformation of other useful functions are summarized in this table. Related terms are Explain inverse Laplace transform. Inverse Laplace transform is the operator which converts the function with complex argument to function with real arguments. This is given as, let's suppose the Laplace transform of two functions as given as, then the Laplace inverse of linear combination of these functions is given as, let's consider a Laplace transform given by. We will now find its inverse Laplace transform. We generally see the denominator of the question first and see if it matches with any basic form. Here the two parts of the question match with basic forms. So the inverse Laplace transform of the first part is given as, the inverse Laplace transform of the second part is given as, the inverse Laplace transform of the problem can be given as. Related terms are Explain the transform of derivatives and integrals. Laplace transform of derivatives says that if a function is continuous and its derivative is at least piecewise continuous, then Laplace transform of its derivative exists. This can be given by, the necessary conditions are, the general formula for the transform of derivative is given by, Laplace transform for integrals is mainly used in electrical engineering or in electrical circuits to solve problems. It states that if a function is piecewise continuous and is of exponential order, then its Laplace transform exists. The transform of such a function can be given by related terms are explain convolution theorem. Convolution theorem is a theorem which states that Laplace transformation of product of two functions is the product of Laplace transformation of the two functions taken independently. This theorem can be given mathematically as the assumptions made for this theorem are. Let us give two functions as. Let's assume that the functions are defined in the interval. Then the convolution of the functions is given by some of the properties of convolution are. The most important property to remember is related terms are explain convolution theorem. Convolution theorem is a theorem which states that Laplace transformation of product of two functions is the product of Laplace transformation of the two functions taken independently. This theorem can be given mathematically as. The assumptions made for this theorem are. Let us give two functions as. Let's assume that the functions are defined in the interval. Then the convolution of the functions is given by some of the properties of convolution are. The most important property to remember is related terms are explain the Laplace transformation of unit step function. A unit step function is also called Heaviside function. The Laplace transformation of unit step function is a function whose value is either 0 or 1 before or after a certain point. This point is known as point of jump. The function can be given as the magnitude of jump is 1. It can be shown graphically as if the jump of discontinuity is at a point A, then the function is given as. This may also be written as. We can show it graphically as the Laplace transformation of the unit step function is given as, where A is the point of discontinuity. Related terms are explain Bessel's equation. Bessel equation is a second-order differential equation which is generally solved using power series by Frobenius method. Bessel's differential equation is written as. In standard form, the equation can be written as. Note that x is equal to 0 is a regular singular point for Bessel's equation. M is known as order of the Bessel's equation. The different order Bessel equations can be written as. The indicial equation is. The solution of the indicial equation is. Related terms are. Of first and second kind. Bessel's functions are the canonical solutions yx of Bessel's differential equation. We generally study the Bessel's equation of order 0. Since m is equal to 0, so the equation can be written as the indicial equation is, the roots are equal since m is equal to 0. So the first solution of Bessel equation of order 0 using Frobenius method is given as, the function in brackets is known as the Bessel function of the first kind of order 0 and is denoted by J0x. The second solution of the Bessel equation of order 0 is, instead of y2, the second solution is usually taken to be a certain linear combination of J0 and y2. It is known as the Bessel function of the second kind of order 0 and is denoted by y0. Related terms are, explain Legendre equation. Legendre equation is a second-order ordinary differential equation given by Adrian Mary Legendre. The equation can also be written in the form, the following condition must hold for a given equation to be a Legendre equation. The equation can further be deduced into the form. This form is the specialized case of associated Legendre equation. The Legendre equation has regular singular point at 1, -1 and infinity. If variable x in the equation is replaced by, then the equation becomes of the form. This form is very useful for solving many mathematical equations. Related terms are, what are Legendre polynomials? The solutions to the Legendre equation are known as Legendre polynomials. The solutions can be found out using Frobenius method of power series. Actually, the solution of the equation are Legendre functions of order n. The general form of solution can be given as, where the indicated terms are Legendre function of first and second kind. When n takes an integer value, these functions are known as Legendre polynomial of order n. The Legendre polynomial of first kind is given by the formula. Some of the initial Legendre polynomials are, the graph of Legendre functions is given by, related terms are, what are the 1D and 2D wave equation? Let's imagine that a stretched string is vibrating. We make two assumptions here. These are, we denote some of the parameters as shown. The wave equation says that at any position on the string, the acceleration in the direction perpendicular to the string is proportional to the curvature of the string. The statement of wave equation can be written mathematically as, so 1D wave equation is the mathematical representation of motion of string when vibration in it are kept in one direction. Now we will move to the 2D wave equation. Consider a thin elastic membrane stretched tightly over a rectangular frame. Suppose the dimensions of the frame are A and B. Suppose we keep the edges of the membrane fixed to the frame. We let some of the parameters as, for a fixed t, the surface gives the shape of the membrane at time t. Under ideal assumptions, one can show that U satisfies the two-dimensional wave equation. So 2D wave equation is the mathematical representation of a sheet vibrating in two directions when its edges are fixed. And it is given as, where related terms are, explain the Laplace equation in two dimensions. Laplace's equation is a second-order partial differential equation named Pierre-Simon Laplace, who first studied its properties. This is an equation that can arise from physical situations. Laplace's equation will depend upon the geometry of the 2D object we are solving it on. The equation is given by, this is often written as, where is the Laplace operator and Sigma is a scalar function. The general theory of solutions to Laplace's equation is known as potential theory. The solutions of Laplace's equation are the harmonic functions. Laplace's equation are the simplest equations of elliptic partial differential equations. Related terms are explain heat equations in two dimensions. Heat equation is the mathematical representation of the function which governs the temperature distribution in an object. For understanding the heat equation better, let's take an example. We take a thin rectangular plate made of some thermally conductive material. Suppose the dimensions of the plate are A and B. The plate is heated in some way and then insulated along its top and bottom. Our goal is to mathematically model the way thermal energy moves through the plate. We define a function. If time is fixed, then the height of the surface gives the temperature of a plate at position X and Y. Now we must assume following things in order to get an equation representing distribution of temperature. So the two-dimensional equation that satisfies all conditions is given by. This is the heat equation in two dimensions. Related terms are explain transmission line equations. A transmission line is a wire with a uniform geometry along its length. The capacitance and inductance of any segment is proportional to its length. We represent as a large number of small inductors and capacitors spaced along the line. For determining the equation of transmission line, we take a short section of line of length delta x. The diagram can be shown as. Let's assume the following things. The capacitor equation can be written as. The inductor equation can be written as. Substituting the two formulas in the above equations, we get the equations are known as equations of transmission lines. Related terms are what are linear partial differential equations? Let z be a dependent variable and x and y be independent variables. Let's assume that z can be expressed as. So the first order partial derivatives can be expressed as. The second order partial derivatives can be expressed as. A first order partial differential equation can be expressed as. This equation is linear if it is linear in P and Q. Similarly, a second order partial differential equation can be expressed as. This equation is linear if it is linear in PQRST. So the linear partial differential equation are those equations which have a linear combination of first-order derivatives of a given relation. An example of linear partial differential equation is, related term is, equations in which all. What are homogeneous partial differential equations? Partial differential equations in which all the partial derivatives of same order and the coefficients are constants are called homogeneous linear PDE with constant coefficient. These are almost similar to linear differential equations. Some examples of homogeneous linear PDE are. Now let's understand it in more detail. Let's assume an equation as. We assume that. So the equation above can be represented as. So the auxiliary equation can be written as. Now we assume that. So the auxiliary equation becomes. Now if two distinct roots exist, then the solution to the given equation is given as. If two equal roots exist, then the solution to the given equation is given as. The related terms are. Explain the definition of a limit. In mathematics, if a function approaches a particular value, as the independent variable approaches to a value, the particular value of the function is known as limit of the function. Let us suppose a function. As the x approaches 1, the value of function approaches 2. But at 1, the value can't be determined. So the limit of the function is 2. The expression for above equation is written as. In simpler form, limit can be explained as fx approaches to L as x approaches to a. Since x approaches to a, so xa is small. Also, fx approaches to L, so fx minus L is small. Let's assume the following conditions. So mathematically, the limit can be explained as. The related terms are. What is continuity? A function is said to be continuous if we can sketch its graph without lifting your pencil off the paper. A function can be continuous at a point and in an interval. We will look each one of them one by one. If the value of the function at a point is equal to the limit of the function at that point, then function is continuous at that point. It can be given mathematically as. Also, if a function is continuous at a, then. Let's assume a given interval from a to b. If the function is continuous at every point between a and b, then it's said to be continuous in the interval ab. Let's assume two functions, fx and gx. Now if the following condition satisfies, then we can say that the related terms are. Explain the derivative of complex function. We have been doing the differentials for real functions. The main motive behind the differentiation of a real function is to find slope of tangent to a curve. But there is not a strong motive behind the differential of a complex function. A complex function is said to be differential at a point if its limit exists at that point. So let a function f, which is complex in a given domain, let C be a point in the domain of the function. This can be mathematically shown as. This is denoted by. We call it the differential of the function f at point A. If a complex function is differentiable at a point, it must be continuous at that point. But the opposite is not true always. Related terms are. Explain the derivative of analytic functions. A function is said to be analytic at a given point if its derivative exists at that point. So there always will be derivative of an analytic function. Let's assume an analytic function f in a positively oriented closed contour C. The derivative of this function is given as, the formula can be remembered by differentiating the equation with respect to z. Derivative of analytic functions are used in, if the function is analytic at a point, all the higher derivatives of f exist at that point. All these higher derivatives are also analytic. The related terms are, explain the sufficient and necessary condition for analytic functions. A function is said to be analytic if it satisfies the Cauchy-Riemann equations. This is the most necessary and sufficient condition for a function to be analytic. Let's assume a function given by. So the Cauchy-Riemann equations are given by. If the function satisfies these two equations, then it would be analytic. Cauchy-Riemann equations are the partial derivative of the real and imaginary parts of the function. These derivatives must be continuous in order for the function to be analytic. Related terms are, Cauchy-Riemann equations. Let's assume that a function is made up of two expressions, u and v. Let these expressions in turn a function of x and y. Now the first order partial derivatives of expression u and v constitute the Cauchy-Riemann equations. So the Cauchy-Riemann equations are given by, or these are the necessary conditions for differentiability and analyticity of a function. If a function doesn't satisfy the equations, it is not differentiable at that point and not analytic. But a function can satisfy the equations and can still be non-differentiable. Related terms are, explain harmonic functions. Let's assume a function given by, let's assume that this function is analytic in a given domain. Then the functions u and v satisfy Laplace equation in that domain. And u and v are known as harmonic functions. So harmonic functions can be defined as, if a complex function is analytic in a domain, then its real and imaginary parts are harmonic functions. The necessary conditions for a function to be harmonic are, the function v is known as conjugate harmonic function of u. The conjugate harmonic function for a given function can be obtained using Cauchy-Riemann equations. The related terms are, explain bilinear transformation. The bilinear transformation is the mathematical mapping of variables. It is the standard method of mapping S-plane into Z-plane. They arise naturally in mapping problems involving the function arctan z. These transformations are conformal in the entire complex plane except at one point. Now let's understand this more clearly. We assume four complex constants as, the condition applied on these constant is, then the function is known as bilinear transformation. Now we multiply the expression of bilinear transformation by. Then collecting all terms at one place we get. Now solving for z, we get. This is known as inverse bilinear transformation. Related terms are, explain the integration of complex numbers. Let's consider a complex valued function ft of real variable, where t is a real variable. This function is assumed to be piecewise continuous. The function is defined in the interval So the definite integral of a complex valued function of a real variable is known as complex integral. Mathematically, it is represented as the integral of real part of the function ft can be given as the integral of complex part of the function ft can be given as. Related terms are explain line integrals in complex plane. It is the integration of a complex valued function of complex variable. The integration is carried out along a curve in complex plane. Let ft be a complex valued function of complex variable. Let C be the smooth curve in the complex plane between A and B. Let the curve C is parameterized by the expression. Then the complex line integral of f over C is given by. The smooth condition of curve C guarantees that Z is continuous. Related terms are explain Cauchy's integral theorem. The theorem was given by Augustin Louis Cauchy. It is an important statement about line integral in complex plane. Let a complex valued function in the complex plane given as. Let the function be analytic in and on a closed contour C. Let first derivative of function also continuous on the inside C. Then accordingly to Cauchy's integral theorem, if a function is analytic on and inside a smooth closed curve C, and the first derivative of function is also continuous on and inside C, then complex integral of the function over C is 0. Mathematically, it is represented as. Related terms are explain Cauchy's integral formula. Let a function f be analytic in a simply connected domain D. Let C be a simple closed contour lying entirely within D. If Z0 is any point within C, then according to Cauchy's equation formula, the contour integral is taken anti-clockwise. Hence, Cauchy's integral formula is the mathematical representation of the value of function at a point inside a closed loop in which the function is analytic. If f is actually infinitely differentiable, then Cauchy's integral formula for its derivatives can be given as. Related terms are explain Taylor series and Lorentz series expansion. A Taylor series is a representation of a function as an infinite sum of terms that are calculated from the values of the function's derivatives at a single point. The concept of a Taylor series was formally introduced by the English mathematician Brooke Taylor. The Taylor series of a function is the limit of that function's Taylor polynomials, provided that the limit exists. The Taylor series of a real of complex valued function fx that is infinitely differentiable at a real or complex number a is given by. This can also be written as function that is equal to its Taylor series in an open interval is known as an analytic in that interval, where a is the point about which we want to find the expansion. Fna is the nth derivative of function evaluated at point A. The Lorentz series of a complex function fz is a representation of that function as a power series which includes terms of negative degree. It may be used to express complex functions in cases where Taylor series expansion cannot be applied. The Lorentz series was named after and first published by Pierre-Alphonse Laurent. The Lorentz series expansion of a complex function about a point is given by the formula, where the meaning of the terms used in formula are. Related terms are explain singular points. The point at which function is not defined or the function is not analytic is called a singular point. Let's take a function given by. The function has singular points at. There are various types of singular point like isolated singular point, non-isolated singular point, removable singular point, essential singular point. We will learn about each of these separately. Let's talk about isolated singular point. If we can find a small real number c such that for if there is no other singular point of function, then z0 is known as isolated singular point. Now moving on to non-isolated singular point. If there is not a point c as considered earlier, then the singular point is known as non-isolated singular point. Now removable singular point. If the function is not defined at z0 but limit exists at z0, the point is called removable singular point. This can also be stated as. Now moving on to essential singular point. If the Lorentz series expansion of the function about the singular point has infinite terms, then the point is known as essential singular point. Related terms are. Explain poles of a system. Pole is a point such that, as we approach it, the value of a function approaches infinity. Let's consider the function. As z approaches a, value of function approaches infinity. The variable n is called the order of the pole. Let's assume that a function has the following graph. We see that at some points the value of function approaches infinity. These points are poles of the function. Related terms are. Explain about residues. Suppose a function has one or more singular points. Inside the simple closed contour C. Each of these points contribute to the value of the complex integral. These contributions are called residues. This approach can be used to solve complex as well as real integrals. The residue for an isolated singular point is given by. The residue at removable singular point is given by. The residue at simple pole is given by. Related terms are. Explain Cauchy's residue theorem. Cauchy's residue theorem is used to evaluate line integrals of analytic functions over closed curves. It generalizes the Cauchy integral theorem and Cauchy's integral formula. Suppose a function has one or more singular points inside the simple closed contour C. Then the integral of the function is given as the combination of contribution of all the residues of these singular points. This is known as Cauchy's residue theorem. It is represented by the mathematical formula. This theorem therefore says that the value of a contour integral depends only on the points inside the contour. Related terms are. Explain about moments. Suppose you have a random variable x. One of the things you might wish to know about x is its expected value. This expected value of a random variable is known as moment of x. Let's understand it with the help of an example. Let us consider X as the number of phone calls a technical support service might receive in an hour. We want to know the expected value of X, so you would know how many employees to hire to handle the phone calls. The expected value of X is called the first moment of X. It is commonly denoted by EX. This is also known as the mean of X. The second moment of X, then, is EX2. The third moment of EX3 and the fourth moment is EX4. These are not used very often, though are usually only the mean and variance needed, and they only require the first two moments. In statistics, there are also sample moments which are similar to averages. Let's take a sample of size n. Then the first sample moment is equal to the sample mean, the sum of the data divided by n. The second sample moment is the sum of the data squared divided by n. Related terms are: explain about moment generating functions. The moment generating function is a real function whose derivatives at 0 are equal to the moments of the random variable. Moment generating functions can be used to easily derive moments. It must be mentioned that not all random variables possess a moment generating function. A probability distribution is uniquely determined by its moment generating function. Let the moment generating function is given by, now this can also be written as